So, welcome back to particle physics and the standard model. This is lecture 20, right. So, as you can see, last time we wrapped up with a solution of the Klein-Gordon equation, which we wrote down in the form of a plane wave, right. So, we explored the concept of the action principle as applied to field theory, and then we saw that there is an art to writing Lagrangians in a Lorentz invariant way such that the equation of motion is satisfied, and we explored the dimensionalities of the fields and the various terms in the Lagrangian and so on, and ended up with a plane wave solution for the Klein-Gordon equation on our way to constructing the Hamiltonian. Yes? Okay. Now, as I was saying last time, this A and B, right, at this moment these are arbitrary functions of the wave vector k. Okay, notice that the argument I have used here is the k wave vector. I did not put time in here yet. I do not have to put time in here. All the time is taken care of in the exponential, in the plane wave solution, right. Another thing to keep in mind here is the field is an operator, right, acting on Fock space, right. So, what is the operator on the right hand side? Where are the operators? The operators are of course again the A and the B. Okay, just keep this in mind. What operators exactly these are, we will see soon. What do these mean? We will see. Okay. All right. Now, once again I want to remind you that we are not interpreting phi as a quantum wave function. Why is that important here? Because it looks like I have written a positive energy solution, right. One of these is a positive energy solution, right. So, I am not sure which sign to use to assign that to. Let us call this a positive energy solution, okay. And this is the negative energy solution, right. So, if you were to interpret the phi as a wave function, which is a mistake that Paul Dirac did, okay, when he formulated his Dirac equation for his equation of motion, he made this mistake. If you were to do that, then it would seem as though the particle state literally has negative energy solutions, right. The field and hence the particle, you literally have particles with literally total energy to be negative. Now, that seems like a crazy idea, correct. That is because it is, alright. So, that is the reason, that is another reason why you should not interpret this as a wave function, you should take this as an operator, okay, and the real physical states come from the action of this operator, okay. So, do not confuse this with some analog of the Schrodinger equation, alright. Now, we have been dealing with a real field, right. At no point did I say we are talking about complex fields, right. It is all about a real field. But I have written a solution that in general looks like a complex number, right. So, I should impose the condition that psi star of x equals psi of x. Agreed? So, if I do that, what happens? Let me write psi star of x explicitly. Let me do this step by step, so you can see what is involved here. The first term is still an A star, right. Generically A is also a complex number, right. And what happened to the first exponential? I am going to flip the sign on that. So, I get minus k dot x plus I omega t, and of course B is also generically a complex number. So I get this, right. So this is all in the exponential, right. This is all in the exponent. Now notice that earlier I had okay, did I make a mistake? No, okay. I want to now write this as a solution such that I have a forward propagating wave and a backward propagating wave. Okay. In other words, in just the second part, I am going to make a change of variables, just a change of, I am just going to go to some dummy variables. Okay. Basically, I am just going to set the k vector to minus k. So what happens if I do that? So let me write that down. In that case, the first term still remains what it is. Right. Now the second term I am going to write like this. So I have a B star, I just set k to minus k, right. So let me put that down. There is an k dot, this minus k has now gone to a plus k, and I have minus omega t, right. But what happened to the integration measure dk, d3k, that has flipped sign, but then the limits also flipped sign, agreed. So the action of both the measure and the limits flipping sign would give me back a plus sign, right. So that is what has happened here, okay, nothing mysterious about that, the sign is still correct. Right. Okay. Now here is the thing, right. If I compare this equation with this equation, right, one thing becomes obvious, right. So over here I had a B star with an I kx minus omega t, and that is what I have here, I kx minus omega t, correct. And then again over here I had a plus I omega t, and that is what I have here also, agreed. So if I want to set these two to be equal, what follows is that I have forced B star of minus k to be A of plus k, agreed. So you can go convince yourself that this is true. Alright. So using this condition now, I can rewrite the solution with just one of these operators, namely I can write it this way, again with all the signs correct. So I am going to pull out the I, okay, plus an A star of minus k e power I k dot x plus omega t this time, right. You see what I have done? But I have just replaced B star of minus k with A of k. Once again I have used dummy variables to flip the minus k to plus k. So earlier when I had a B of k, I am just using A star of minus k. Okay. Now once again, to make this look easier on the I, once again I am going to do the dummy variable trick, so that At the end of the day, I can write the solution in this compact form. It is just an A of k, and I am just going to say ikx plus A star of k, and I am just going to say e power minus ikx. What is kx? Kx is nothing but the product of two 4 vectors. Okay? So, that in a nutshell is the solution. Now, I did not talk at all about the measure yet, right. So, I am not going to do this in class now, okay. It involves some algebra that involves properties of the Dirac delta function, but I encourage you to go look this up in Srednicki's QFT chapter 1, where he derives this measure for you. Okay. At the end of the day, I am just going to write down the result here. This measure, which you want to be Lorentz invariant, turns out to be nothing but d cube k over omega. Okay. But for reasons of convenience, you will find that it is not just omega, it is 2 omega, but not only that, there is another factor of 2 pi cubed, which will help calculations go smoother with normalizations and so on. Okay. So, this whole thing, just to remind us that it is a Lorentz invariant quantity, is often written as dk with a tilde on top. So, when you see this, remember that it is a Lorentz invariant measure, and you can also convince yourself that the dimensions all work out. Okay. So, what I am going to do now is just import that notation and manipulate this a bit, so that I just write within that red box. I am just going to write dk tilde. Okay. So, it looks even more compact now, right, even more memorable. Excellent. So, that is a general solution to the Klein-Gordon equation. With that, we should now be able to write down the Hamiltonian in a compact way. Okay. So, how do we do that? First of all, I can write the conjugate momenta, right. To write down the Hamiltonian, first I need the conjugate momentum, right. So, that is what this is, again complete analog of classical mechanics. Agreed? So, from that I can write a Hamiltonian. To be even more precise, it is the Hamiltonian density, just like the Lagrangian density, right. So, that is why I am writing a curly h. The Hamiltonian density is, oops, it is, in a sense this acts as the kinetic energy, and I subtract the Lagrangian. Again, just to be explicit, h is the Hamiltonian, curly h is the Hamiltonian density. Okay. Now, in our case, right, what is this pi? What is the conjugate momentum field? Go back to the Lagrangian and you will see expand it in terms of the time derivatives and the space derivatives, and it is easy to see that it is just phi dot, as you would expect again from a classical mechanics analogy, right. Okay. That is the conjugate variable, so that the Hamiltonian has simply become pi square over 2, or let me just write this way. So, let me just write phi dot square of x over 2 plus the grad phi squared plus half m squared phi squared. Am I forgetting something here? One of the most important things is the final term minus omega naught, the constant energy density term, right. Now, notice that this looks good because this seems to give you an energy density that is positive definite, correct. It does not have to be, I mean it does not have to, it does not follow immediately, but at least the first few terms are positive definite, right. So, it shows that the energy density, which is slightly different from the Hamiltonian, right, the formula for that has a chance of being positive definite, although the Hamiltonian density itself could actually be negative because you have a final negative term, right. Okay. So, now once again I am going to skip some algebra, I am going to take this solution, okay, and plug it into the Hamiltonian, and once again I encourage you to go through Srednicki for the algebra, and I am just going to present to you the final expression and convince you that it makes sense, okay. So, I am going to write down the Hamiltonian, not the Hamiltonian density, because that is more instructive to see, right. One thing I know for sure is that I can integrate this term over volume, so that for whatever volume I am thinking about, I can right away write down the first term, agreed, minus omega naught times the volume of the system that you are thinking about. The other terms take a while to get hang of, that is where you should go look at Srednicki for the algebra, but when I write down the final form it will look familiar to you. In the end it would look like an A star of k and an A of k, okay, plus an A of k A star of k. Okay, does not this look familiar? Where have you seen something like this before? It already reminds us of the harmonic oscillator, correct, in quantum mechanics. Remember how the Hamiltonian looked there, right? The Hamiltonian was like this, right, up to some I hope I did not miss any factors here, but I think this is correct, right, or maybe it is an AAA dagger. So, you should check this. Agreed? Okay. In other words, the A's are they resemble the ladder operators that we have seen in the harmonic oscillator problem. That is not a coincidence, okay, because indeed these A's and A stars are something like ladder operators, except they are creation and annihilation operators. The ladder operator in quantum mechanics took you to an energy level one step above or one step below, right. A star promoted the state to an energy level one step above, A took it one step below, right. In a very similar vein, the creation operator and the annihilation operator creates a state, creates a particle, okay, at a given momentum. So, for instance, if I took an A dagger, and notice that I have switched from A star to A dagger already, right. It is perfectly consistent to do that. So, if I took this operator, right, and acted on what is known as the vacuum. What is the vacuum? It is not the literal vacuum of space, okay. It is the ground state available in a quantum field theory, okay, the state with the least energy, but also the state with no particles in it. So, if I did this, then I would create a particle state, let me call it that, with a momentum k, okay. That is what this means. I can also have written the annihilation, these operators in with space time labels. That would just mean that if that operator acts on the vacuum, it creates a particle state at that space time position, okay. But here we are in momentum space, so you create a particle state with the momentum k. So, if the A dagger corresponded to an electron, then this is exactly how you make an electron. This is exactly how the quantum field or the quantum operator creates an electron with momentum k, okay. So, then what would this be? If I took the annihilation operator or the destruction operator and acted on the vacuum, what would happen? That would just lead to a state of nothingness, okay. So, this just basically annihilates the ground state itself. That is kind of how you define the annihilation operator, okay. So, similarly, if the annihilation operator acted on a state that you have created here, it goes back to the ground state, the vacuum, okay. So, with that intuition, the following commutation relations should not come as a surprise to you. Same intuition as ladder operators, okay. So, I have this and I have agreed, and most importantly I have the commutator between A and A dagger with two generic momentum labels to be, first of all, do you agree that there is a delta function, right, and then there is a suitable normalization which turns out to be this with an omega. Do you agree? This is how they should commute from our intuition about how A and A dagger commute. in quantum mechanics, in non-relativistic quantum mechanics. Okay. So, we can now make use of that and rewrite the Hamiltonian here, right. I am going to plug this in and rewrite the Hamiltonian as the following. So, the Hamiltonian is now, once again I have the measure there and I am going to use the third commutation relation to switch between A and A star or A and A dagger and put in a delta function over there, and that also gets rid of the half, correct. So, that I get A dagger, excuse me. So, first I have an omega sitting out in front, which I still have to include. So, there is an omega, A dagger k, A of k. Is that all? No, I still have the minus omega naught v, right. So, let me write that, but even that is not the whole thing, right. I still have the delta function that I should integrate over, correct. So, the delta function I am gonna, after integration I am gonna write it this way, and since I have integrated over the volume, it is this. So, it is the term in the integral plus some constant term. So, how did I get there? What I did was I made use of the following relation in the integral okay. So, this is an identity that I made use of. This is a trivial identity, right. That is one way to define the delta function. You take the Fourier transform, right, of just the phase e power I q dot x. In particular, since now I have a delta cubed of 0 of the 0 vector, because I am acting on the same momentum, right, both k and k prime are the same. So, k minus k prime is 0. That means what I had was a delta cube of 0, correct, with a suitable normalization scheme 2 pi cube, right. So, I have now interpreted since for q equal to 0, I have interpreted this term as a volume basically. That is what I have done. Okay, it is perfectly valid, right. Remember the delta function is in momentum space. So, it is a 1 over k cubed, but if k is 0, that is the entire volume of the system, agreed. So, that is what I have plugged in here. Okay. Now, what is the value of this epsilon naught? It is not epsilon naught, it is just E naught, okay. I have just written a curly E. So, let us just call it E naught. What value could this E naught take? Okay. We have integrated over some modes of the the scalar field, right, and ended up with this volume, right. So, let us write that down explicitly. E naught in those manipulations is basically this term, and then I had an omega, agreed? We had an omega sitting all over the place, right? Ultimately, and okay, so there is something I missed here. So I should have, there is already an omega sitting here. At the end of the algebra, to get the units right, the Hamiltonian needs to have units of energy, right? So there is an omega here, omega being the on shell energy, right? Square root of k square plus m square. So it is always this energy that we are integrating over. So that omega goes along for a ride, and in the epsilon naught, sorry, in the E naught, I have just integrated over the momenta. Okay. So what is the physical meaning of this? This epsilon naught is nothing but the 0 point energy of the system. Now what is the system made of? When we wrote a mode expansion for the field, right, we have in some sense done a Fourier expansion, right. In other words, we wrote the field as a mode expansion of various frequencies, agreed? And okay, and in quantum mechanics, and quantum field theory very much involves quantum mechanics, there is no what is the lowest energy level? So we saw it even here, right? So now we know it is not a dagger. Even here we saw that the lowest energy level is not 0, correct? There is always some minimum energy that your system would have, correct? Where does that come from? That is a consequence of Heisenberg's uncertainty principle. Right? There is always a 0 point energy. We already saw it in the case of the quantum mechanics harmonic oscillator. That is what we are seeing over here also. Here also you have written the scalar field as a mode expansion, and so you have written it as a combination of harmonic oscillators, right. You will notice that in everything in field theory takes the form of harmonic oscillators, okay. And that means this system also has a 0 point energy in the Hamiltonian. That is what we have expressed with this integral, okay. So I am going to wrap up by giving an expression for this 0 point energy, and in the next lecture we will take up the question of why this is very problematic, okay, for the universe that we live in at least. So I am going to write down an expression for E naught and then explain to you its physical meaning. Since there is an energy density, I am going to assign some lambda with mass dimension 1, and energy density has mass dimension 4, right, energy over length cubed. I can now rewrite this in this form. So what does this mean? It means the modes that I am expanding over, sorry, the modes that I am integrating over, right, the d cubed k. If you think about it for a second, I cannot take the limits, maybe I can start with a 0, there can be a 0 momentum mode to the field, but it makes no sense to go all the way to infinity, right. So I am going to put an x here to show that it is wrong, or I just write it is wrong to go all the way to infinity. Why? Because nothing in physics is really infinite, right. There are no real infinite momentum objects in the universe, right. So, the validity of all this is limited. So, this entire treatment is very probably only valid up to some cutoff in the momentum, correct. These mode expansions cannot go all the way to infinity, everything would just blow up, right. If you just have to, if you have infinite momenta in every single field, they will just carry infinite energy and things are just going to blow up all over the place, things are going to get very messy. So, it makes sense that there is a cutoff to the theory, there is a cutoff to what are the momentum modes that you can put in for the scalar, right. So, that cutoff is what I call lambda, alright. So, this lambda is nothing but, in other words, an ultraviolet cutoff. Why ultraviolet? Because this happens at large energies, nothing to do with the real ultraviolet of the electromagnetic spectrum, okay. People just use the word ultraviolet cutoff and infrared cutoff to denote a cutoff of the highest momentum modes and the lowest momentum modes respectively, okay. And we know that in nature there is one ultraviolet cutoff that we cannot run away from. We know that the highest energy scale up to which quantum field theory should work is what is known as the Planck scale, okay. The Planck scale has values of this 1.2 times 10 power 19 GeV. The important thing is to remember 10 power 19, okay. What is the weak scale or the Fermi scale? That is about 100 GeV, right. For comparison, this is 17 orders of magnitude larger. So, what is the significance of the Planck scale? That is where we believe that gravity takes over as a quantum theory. We do not really know what the quantum theory of gravity is, but basically if you just took Newton's constant, right, and worked out the dimensions, you will find that it is exactly 1 over m Planck square. So, from Newton's gravitational constant we know what the cutoff scale is for all the quantum field theories that we are working with, such that around there gravity takes over and then we really do not know how to describe quantum field theories beyond this scale, okay. This also corresponds to a very tiny distance scale, alright. So, what we will do in the next class is we will plug in this Planck scale as the cutoff value and calculate what the energy density is coming from a simple quantum field theory like the Klein-Gordon theory, and see that this already has disastrous consequences for theoretical physics, okay. So, that is what we will do in the next class, I will leave you here. Thank you.